Moving on from our discussion of exponential growth, let's talk about exponential decay. We're still talking about an exponential function, so it's still going to be in the form of y equals a b to the x. And let's describe our variables once again. So think a is the starting letter of the alphabet. A is our initial or starting value. So it's our starting cost or our starting population or our starting money in the bank before interest applies, whatever the situation is that we're looking at. B, before B was 1 plus our growth rate, but this time I don't have a growth rate. I have a decay rate. I'm going to have less of something every time. And so B is going to be 1 minus my decay rate. And in this case, decay rate is going to apply to things like maybe the value of our car goes down every year. So that's called depreciation, where let's say each year, I don't know the actual numbers, but it's something like each year your car is only worth 90% of the value it had the year before. So the value goes down by 10% each year. Or we have a radioactive material that slowly decays and turns into a different kind of material. So after each half-life, we call it, after a certain period of time, only half of the original amount of plutonium or uranium or whatever is remaining. And x is our variable for number of periods. So how many half-lives have occurred, how many years have occurred during which your car has depreciated in price, and that kind of thing. What should we talk about next? Like before, let's work through an example where we have an equation. We'll find our table of values and we'll graph. And then we'll talk briefly about the applications, and then we'll dive into some word problems related to growth and decay. So let's start with our example equation. And let's say I have my equation of y equals, and let's do kind of a basic car example. Let's say my car is worth $1,000. Most cars are probably worth a little more than that, but I want to keep our numbers pretty basic. I don't want to work with like a number of 40,000. And let's say our B value is 0.85 to the power of x. So let's describe what each of these numbers tell us, and then we'll work on our table of value and our graphs. So first of all, my A value is equal to 1,000, and that is my starting value of the car. So when x is equal to 0, when no time has passed, when I've just received it, so presumably this is what I've paid for it, it has a value of $1,000. B is equal to 0.85, and remember that B is equal to 1 minus my decay rate. So we're just going to focus on this equation right here, and we're going to figure out what is my decay rate. How much is the value of my car going down by each time? So we're going to solve. So I'm going to move different ways of solving this, but I'm going to move the 1 over to this side. So I'm going to subtract 1 from each side. So I'm going to have 0.85 minus 1 equals a negative decay rate. 0.85 minus 1 is negative 0.15 equals negative decay rate. And now to get rid of the negatives, I just divide each side by -1. Or you can just think of it as they just cancel out. So it turns out my decay rate is equal to 0.15 or 15%. So let's describe that in words. So you don't need to do all this work every time you have a question like this. But I mean, we're just learning about this, so I want to show as many steps and describe as much as possible. So car loses 15% of its value each year. And x is just going to be the number of years that have passed. So that's what our equation means. Hopefully you'll get a feel for understanding that. So anytime my B value is between 0 and 1, it's going to be decay. So let's actually write that off to the side somewhere. When B is between, so our notation, so 0 greater than B, or B, 0 less than B, B less than 1. So what that means is, I'll write it in words, when B is between 0 and 1. So when B is between 0, and 1. So it can't equal 0, because then we're multiplying by 0 and our graph just doesn't go anywhere. It's just always 0. I can't multiply by 1, because multiplying by 1 doesn't change the value. If my b value was 1, so if I had 1000 b value of 1 to the power of x, I'm just multiplying by 1 over and over and over again. The value never changes. So my b value cannot be 1, but it can be close to 1. So when b is between 0 and 1, we have exponential decay. All right, so we've talked about our equation. Let's find our table of values. And I'm not going to do the ratio test this time. We could if we had to, but we already talked about that in the previous video, so I'm just going to move on from that for now. So let's find our table of values. As before, when dealing with exponential functions, I don't really care about negative x value, so I'm going to start at 0, and let's go up a few years. Let's go 1, 2, 3, and 4. Now let's find our y values. So I'm taking my x values, I'm choosing values, I'm putting them into my equation machine, and I'm calculating my y values and writing them in the table here. So let's do that. My equation is 1000 times 0.85 to the power of x, but instead of x, I'm putting in my actual value, so to the power of 0. I know anything to the power of 0 is 1, and I just focus on the exponent and its base. So I just focus on this part first. So 0.85 to the power of 0 is 1. 1 times 1000 is 1000. And hey, that's my a value. So let's just make a quick note to remember that. And then I'm going to do my next calculation. So 1000 times 0.85 to the power of 1. I'm going to need my calculator for this. So 0.85 to the power of 1 is 0.85. 0.85 times 1000 is 850. I guess I probably didn't actually need my calculator for that, but it doesn't hurt. Next one, 1000 times 0.85 to the power of x, but I'm choosing my specific value for x, so I'm going to do 2. And calculated, that's going to give me a value of 722.5, or $722.50. And again, 1000 times 0.85 to the power of 3. And remember, if you just want to punch this in your calculator and just write the answers, that's fine. You do not need to show all this work, but I want to be super clear as I explain this to you so you know where the numbers are coming from. And when I do this calculation to the power of 3, I get a value of 614.13. And then again, at year 4, 1000 times 0.85 to the power of 4 is going to give me a value of $522.01. And we could continue on, but that's enough to get a pretty good graph. And I only have so much room on the page. All right, so we've successfully gone from an equation to a table of values. Hopefully you're getting familiar with that idea. We've practiced it in our quadratics unit. We are practicing it in our exponential unit. So it's kind of one of the basic skills you're going to want to learn and have throughout this course. How can I take an equation, turn it into a table of values, and turn it into a graph? And in a future video, we'll talk about going backwards. If I start with the table of values or I start with the graph, how can I find the equation? And I promise you it's not that hard. You already have the basic skills and building blocks to do that. But for now, we've started with the equation. We've found our table of values. Let's go ahead and make our graph. So my x-axis is going to go from 0 to 4. So it only needs to be positive. Makes my life a little easier. So x, 0, 4. Usually start at the end, go through the middle, and then 1, 2, 3, and 4. All right. And my y values are going to go up to 1000 and go down to 522. So I could make it's called a truncated graph, where I just focus on this area and I put a squiggle to show that I jumped from 0 to 500 in there. Normally I don't bother though, so I'm not going to do that right now. I just want to mention as an aside that that is possible. Instead, I'm going to focus on the whole thing. So I'm going to have 1000 and 500 and 750 and 250, and that's going to be good enough. We are just graphing by hand. I mean, it's going to be very difficult to show exactly, like 614.13. So like, don't worry about that. Just kind of get approximately the right shape. So remember, each of these represents an ordered pair. So this is an x value and it's matching y value. So I know that when x is equal to 0, y is equal to 1,000. So let's make our first dot. That one's done. Our next one, when x is equal to 1, y is equal to 850. So that's going to be somewhere around here. Yeah, somewhere around there. When x is 2, y is 722. So that's going to be somewhere around here. When x is equal to 3, y is 614. So somewhere around here. When x is 4, y is 522. And that's going to be right around there. And now we can go ahead and connect our dots. And so my graph isn't perfect, so I'm actually going to tidy this up a little bit just so we can see the curve a little better when I draw my dots. And I'm not cheating. If I'd done this properly, it would look proper. I just didn't match the points up quite neatly enough. So my curve should look something like this. So exaggerated is going to be like this. To make it a little more accurately, it's going to look something like this. Oops. Don't want to curve back up. It's always going down. So something like that. So it's gently curving down. It looks kind of straight just because I didn't scale my graph big enough. If I'd made my x-axis bigger, we'd see more of a curve. But we've already graphed it. We're stuck with it now. It's good enough. All right, so we've successfully made our graph. Oh, and I forgot to label my y-axis. Very important. And that looks pretty good. So we've successfully gone from an equation to finding our table of values to sketching our graph. And I think that looks pretty good. The final thing I want to discuss, and I've kind of touched on this already, but I want to write it down in our notes, is application. So when are we going to deal with this kind of graph? What kind of word problems are we going to need to solve? One of the most common ones we're going to look at is decay of radioactive material. And I talked about this briefly in class the other day. Basically, inside the nucleus, we have our protons and our neutrons. And basically what happens is something inside happens. And there's different ways of thinking about it. But basically you're going to lose some particles. So you can imagine like a proton goes flying off. And it's a little more complicated than that. But basically your number of protons is going to change. And when your number of protons changes, that changes the identity of your atom. So it's not like atoms are flying off of your metal, but radioactive particles are, and that's what makes it radioactive. There's stuff shooting out of it. That's why it's dangerous. And so the type of material that's in your sample is going to change. So if it started out as 100% uranium, as time goes on, it'll still be mostly uranium, but it'll be something else and as well. And as a lot of time goes on, eventually there's almost no uranium left. It's all been converted into other different types of metal. Another common example is depreciation. Depreciation of value. So there's a financial connection for us. I know this class was particularly interested in finances, and we'll talk about this stuff more as we go. Basically, we spend our first couple weeks building our skills using exponents and exponential functions, and then we can start to apply that to financial applications in our coming weeks. But depreciation of value, like I said, with things like a car or a computer, basically any kind of consumer good, it's worth a lot when you buy it originally, but as soon as you drive the car off the lot, as soon as you take the sticker off that graphics card or that Nintendo Switch, or as soon as you build your computer and start using it, those parts lose their value. And as time goes on, they're going to become worth less and less because there's always new stuff coming out. So if you paid, $1,500 for your iPhone last year, even if it's still in like mint condition, there's no way you're going to be able to sell it for $1,500 right now. And there are exceptions. So if you guys are interested in electronics, you might know right now that like a lot of electronics are really keeping their value or have gone up in price. So if you want to buy like a graphics card or a processor for your computer, Prices have actually gone up over last year because there's a shortage, because people not working for a while when the pandemic started, due to higher demand for consumer electronics. People are at home, they have more time, they have more desire to play video games, to build computers and stuff like that. The producers just can't keep up. And so because of the special circumstances in the world right now, some things that would normally depreciate have actually gone up in price. But that's pretty abnormal. Usually when you buy something, it goes down in value for a long time until it becomes rare. So, if you want to buy a used car from 10 years ago, well, it's not going to be worth very much. But if you want to buy a used car from 100 years ago that still runs, well, that's going to be worth a lot. But those are exceptions. Generally, things just decrease in value as time goes on. The other situation we might want to consider is another example we might see. These are the two most common, to be honest, but atmospheric pressure is another example. So as we climb, if we climb a mountain or go up a big hill or go to another part of the country that has a higher elevation, pressure comes from the amount of air on top of you. So if this is our atmosphere, I like science, so let's have a little explanation here. So this is going to be our atmosphere, and this is the ground. Basically, when you're sitting at the ground level, there's a whole lot of air on top of you. It's kind of like being at the bottom of the pool. You can feel that pressure on you. And I mean, you can survive it, it's fine. But there's definitely a noticeable feeling there. That's what we feel every day. We just don't notice it because we live in it. We're used to it. But if I start to climb a mountain or a hill, let's say we go up a really, really tall mountain, even taller than Mount Everest. As we go up, there's going to be less and less air on top of us. And so we experience less and less air pressure. So atmospheric pressure will change as you go higher, and it changes in terms of the curve or the shape would be, pressure versus height. As height increases, pressure decreases until you're in space and there's like no pressure. And so that's going to make a curve. I'm not making these curves curvy enough. They look like straight lines, something like this. So as you go, eventually you're going to have like almost zero pressure in space. That is an example of exponential decay. We probably won't see any questions like that specifically, but just so you know, like, why do I need to know this? What is the point? What kind of stuff in my everyday life would be described by exponential decay? Dealing with pressure or air pressure and height is one example of that. Overall, hopefully that gives you a general impression of how we work with exponential decay. Just like before, in each case, the key ingredient is that there's a common ratio. So if I'm looking at my y values, each time I find the next y value, I'm multiplying by some number. And in this case, that number is less than 1. So every time I go from 1,000 to 850, I'm multiplying by 0.85. And to find the next number, I'm multiplying by 0.85. And to find the next number, I'm multiplying by 0.85. And to find the next number, I'm multiplying by 0.85. Multiplying by the same number each time to find the next number is what defines this being exponential. And it also means that if we do our common ratio test, which I didn't bother in this case, but we saw it up here, if I do my common ratio test, I can find my b value. So maybe let's talk about that really quickly as a preview for a future video. How can I find the equation? What if I didn't give you the equation? What if I just gave you a graph or the table of values? Well, let's think about what our equation looks like. Y equals a, b to the x. Y and x are just variables. They represent all the possible numbers we can plug in there, so we don't have to solve for them. I just need to figure out my a and my b. A is my starting value. So on my graph, it's my y-intercept. Or on my table, it's my y value when x equals 0. And my b value is just my common ratio. So in order to find that, I just take a y value. So let's say I take the third y value on the list, I divide by the one that came before, that's my b value. Or if I take the second y value in my list and I divide by the one that came before, and I get the same number, that's my b value. And so we'll go into this in more detail and do some examples later. But as a quick preview, that is how we find the equation. And it's not too bad because we've already done all these things previously. We just have to apply them in a new way. So you can think about that a little bit, mull it over in your mind, and know that we will be working with that in the future.